Imagine you're on a field for whatever reason, and in front of you is a thin wall. Imagine you have a soccer ball. Imagine you kick said soccer ball towards the wall. What happens to the ball?
Well, it's gonna bounce back.
Correct! But what if the ball isn't a soccer ball, but actually a stupid parallel for an electron?
Run that one by me again?
Well, I mean, what you said is correct most of the time, but sometimes the exact opposite will happen. The ball bound for the wall will just pass straight through it.
Wait, what?
If I said because science, would that be enough for you?
No, definitely not. Wait a minute, hold on here. Was that just some convoluted metaphor in which you make reference to a crazy, complicated, and abstract scientific topic in mundane terms, so by the time I realize it's a crazy scientific topic, I'm already sucked in and I have to listen while you explain it?
And if I said it was?
I hate you.
Well, it was. And the crazy abstract concept is quantum mechanics. But before that, you need to understand an even more confusing concept.
More confusing than a ball phasing through matter. I'm making a good case for the whole not hating you thing.
Oh yes, and much more. Particle wave duality levels of confusing.
Patrick Wade, who to what?
No. Particle wave duality, where stuff behaves as both particles and waves, but is actually neither.
Yeah, you lost me.
Okay, think about it this way. You have a hole in a sheet of cardboard, and you start spraying sand through it onto a wall that's behind it. What pattern do you expect to be on the wall?
I don't know, Kermit the Frog doing the conga.
What?
Nothing. Look, a little spot where the sand went through the hole will be on the wall.
Yes! And if you were to, I don't know, say half submerge this hole in water and send some waves through the hole, what pattern would you now expect to be on the wall behind it?
A torn up sheet of wet cardboard. But the answer you're looking for is a wave spread out over the wall?
Yes, again. Now let's make another hole in the sheet.
Oh boy, let's!
Okay, well, now we'll send a wave through both holes simultaneously. What do you expect?
Well, the wave will come out through just both holes and create a new but predictable interference pattern with itself along the wall.
Did you just talk smart?
Yes, now carry on. You kicked my soccer ball through a wall a minute ago, and I have to go get it.
Well, you're correct. The waves interfere with each other constructively and deconstructively. If the two waves constructively interfere when they hit the wall, then the wall will be hit with full force. But where the two destructively interfere, the wall is simply hit with a calm wave. If you did this with light, then you would see a mixture of light and dark patches that line up with this.
Great, light is a wave. Case closed.
Well, not exactly.
Okay.
Let's look at this experiment again, with something like sand again. How about electrons?
Electrons are sand. Wonderful. Now it really makes sense.
Well, yeah, sure. I mean, electrons are small, little marbly things that make dots on the back wall when they're fired through the holes.
Sure. Little marbly things. Dots on a wall. Right.
Well then, if you fire these electrons out and into the holes, what do you think will happen?
The electrons will hit the wall through the holes they were just fired through.
Excellent! You win the I was completely wrong award. What we actually see is a pattern similar to that of the waves.
What? But there are dots where there aren't even holes.
Okay then, fine. Let's do this again. This time, one electron at a time.
2 hours later. Are we done yet?
Yup. Are you ready for the grand reveal?
Can I go now?
Ta-da!
Wait, but how did they get there?
Simple. That's where the wave hits.
But electrons aren't waves.
That they aren't, no.
I thought we said they're particles.
No, they're not that either.
But isn't that part of the whole point we just established?
No. Remember, I told you, everything is neither a wave nor a particle, but displays properties of both.
Okay, fine. But how does that explain these dots? If the electron, singular, is acting like a wave, then why does it do this? Shouldn't it just come out like this? And if it was acting like a wave, then why does it still make a dot on the wall? And why does my head hurt?
Okay, well, first of all, you're thinking about this wrong. While the electron is moving, it moves as a wave would. But not just any wave, a probability wave. A wave of where the electron is most likely to be.
So hold up then. Are you telling me that we don't actually know where the electron is? That all we can do is use math to kind of sort of guess where they're likely to be and it looks like a wave?
Well, in a manner of speaking, yes. And the reason why the double wave pattern is seen is because when the electron probability wave goes through the holes, they create new waves themselves according to the Huygens principle. Then these waves are what interfere with each other.
But that doesn't make any sense. The wave interferes with itself?
Yup. Welcome to quantum mechanics. You don't have to like it, but that's the way it works. To our knowledge.
Oh, please tell me this ends here. Wait a second. We haven't talked about quantum tunneling yet. What does this have to do with quantum tunneling?
Well, particles on the quantum scale behave in ways that you would never expect.
Like a soccer ball going through a wall? Speaking of which, it better still be over there when we're done.
Well, precisely, and generally speaking, or rather classically speaking, an electron cannot penetrate a barrier or field of greater energy than that which itself possesses. Think of this all as a ball not being able to break through a wall without enough force or energy. Should a particle encounter such a barrier, it would just be repelled. Just as a ball would bounce back, so too would this particle.
So the ball comes back because you didn't kick it hard enough for it to go through a wall. Okay, fine, that makes sense. But what now?
Well, as we saw in the double slit experiment, things aren't just a particle or a wave, but rather some mixture of both. So while our electron is moving through space as a probability wave, it might just come across this barrier.
And bounce back.
Well, usually that is the case, yes. However, as you can see, the model, whose function is to describe the probable position of the electron wave in question, also shows that upon encountering the barrier, there is a finite amount of positional probability that it's on the other side of the barrier. So, given that God rolls a natural 20 on his electron position check, then the electron will actually be on the other side of the field than what it was previously on.
And here I thought God didn't play dice. So it just poofed its way from one side of the barrier to the other? How did it get there? It just traveled through the barrier?
Well, the electron could also be in the barrier sometimes, although that's unlikely, but as per your question, it didn't really travel at all. It's simply there.
I think I see what you're saying?
Well, to put it in other terms, without traversing the area of the field, it finds itself on the other side of the field immediately, simply because that is where it is.
So it travels faster than light?
Yes and no. It doesn't move at a speed faster than light, but the distance it changes in the time it changes is.
So it teleports in a sense. Pops from one place to another without going through the places in between them. Kind of like a tunnel between the two, maybe.
Well, yes, in a sense, but this is all just one interpretation of the results of scientific research.
So much for modern science.
But this is modern science. This is exactly what our community is trying to figure out. And even without knowing for certain, the concept of quantum tunneling is widely used.
Hang on, how can we use something we don't fully understand?
Well, do you fully understand your own brain? Many scientists don't, and yet there's not a person alive not using their brain.
I'm not so sure about that one. Cool, so if this has already happened, when can I shave my head, order Mr. Kusher to warp factor 5, and make it so?
Oh, but we're already coming close, and we already have to some extent. Quantum tunneling can apply to more than just energy barriers. Imagine two very close metals that aren't touching. That tiny space between them acts as the barrier in this case, and electrons travel from one metal to the other. Now imagine the system is part of something we call a transistor, and that may or may not be one of the most integral parts of all modern electronics. That touchpad on your smartphone, the phone itself, your computer, and most other electronics you make or use transistors and, by extension, quantum tunneling. It's a regular event in your life.
Wow, I never knew. I guess that convoluted analogy turned out for the better. Hooray for science!
Really? You mean it?
Not in the slightest. You owe me 5 minutes and a new ball.